Professor Barry Sanders. He is a faculty at University of Calgary. Today he'll tell us about his quantum work at RRI.
Okay, thank you for the kind introduction. And yes, this is the last talk of the last day of a long week. And I appreciate the previous speaker stayed to time. And yeah, last talk, last blah, blah, blah. Okay, thanks. And the previous speaker stayed to time, and I'll do the same. So we won't run a minute over time. What I'm going to talk about in this last lecture is just focus on the work that I've been doing with RRI people in the past few years while I've been here, Vajra, and even before. So I'll start off, I'll discuss the work I've been doing with Urbasi Sinha and her group, and then I'll go on to the work with Andal Narayanan, who's not here today. She's on leave at the moment. So I'll talk about both sets of work. It's kind of an overview. So I'll just go through each of the papers that we had together and then briefly summarize each one. And I'm very happy to take questions as I go through it. And I must say, it's been a real pleasure to be here. My term is not ended. I think I still have till March 2023. So I'm still an RRI visiting faculty member for a few more months, and savoring every minute of it. And it's great to have all of you as colleagues. Here's the RRI symbol. This is University of Calgary. So I'm using University of Calgary slides. And this is the Vajra scheme that's been supporting me in recent years. Okay. Okay, so the first one that I'll talk about is a topic that certainly I was thinking about for years, and I talked to Urbasi and about this idea that there's a standard view in quantum optics that the Hongo-Mandel dip is a quantum effect, and I'll explain a bit more. The idea of the Hongo-Mandel dip is that if you send a photon in one port of a 50-50 beam splitter, one that equally reflects and transmits, and a photon in the other, then what comes out is 2 this way, 0 this way, and vice versa. And then classically, the photons will randomly reflect or transmit. And so there's a 50% likelihood of coincidence classically in the perfect case and 0% probability of coincidence in the quantum case. And ever since Hongo-Mandel's work in the 1980s, this has always bothered me because I could always see in my mind how it would work classically. And so, to me, the kind of the fundamental idea of quantum mechanics is wave-particle duality, complementarity, that kind of thing. So then Urbasi and I talked about this idea, and we figured that we would write this up. And we wrote up the paper. It's well received. The problem getting the work out, for decades I'd been talking to people, and everybody thought the idea was wrong. And then, of course, when you start to write a paper, so we wrote this up, and then when we wrote it up, the referees just say, "Oh, obviously, this is the case. It's not quantum." But I sampled everybody, and actually, the only person who said yes, it's right that the Hongo-Mandel dip is classical was Alain Aspect. He's the one who just won the Nobel Prize a few weeks ago, and he told me back before we finished the paper, he said he would have thought my statement was wrong just 2 years earlier, but he'd been thinking about some atom optics thing and realized that it wasn't the case. So this is my story, that this whole thing about the Hongo-Mandel dip being classical, before we wrote this up, and I sampled scientists, they all said, "No, you're crazy, it's all quantum." And then after it, everybody says, "Oh, this is obvious." That's where it happened. But I'm very proud of this work that we did together. I only did theory, everybody else in the list did the experiment, which is the hard part. And so here, the paper's near 100% 2-photon light coincidence visibility dip with classical light and the role of complementarity. So it captures the message that you can get classical photons, those are just pulses of light, and get 100% dip, not the 50% dip that quantum optics textbooks tell you. And then the key point of knowing that the Hongo-Mandel dip is quantum is you have to do a complementarity test. You have to see if you set up the conditions to see 100% dip, then you won't get the wave-particle duality. And so we wrote here, the Hongo-Mandel effect is considered a signature of the quantumness of light, as the dip in coincidence probability using semi-classical theories has an upper bound of 50%. Here we show theoretically and experimentally, with proper phase control of signals, classical pulses mimic Hongo-Mandel dip. We got experimentally 99.635% dip using microwave fields. And it's actually one of the nice strengths I found at RRI. There's an inherent interdisciplinarity. So, there's the expertise in optics, but there's also a different expertise in microwaves here. And through combining that, it was possible to work with microwaves. And people tend to agree that microwaves, for all intents and purposes, free space propagation are classical. So we showed the effect. And then this is just some sampling of the experiment. We have the microwave and the infrared photon case. These two pictures I just grabbed a few minutes ago from published paper. I'm using a short DOI. So DOI is the digital object identifier. DOI offers a hash service that shortens them. So if you plug this into the 10/JK3W into the DOI service, the source of this will pop up. So I'm not plagiarizing, it's a reference. And this is the idea of a Hongdon mantle dip. You send a photon in here, and then you have detector, measure the coincidence. And then what you find is if you plant the beam splitter at a sweet spot where both photons arrive at the same time, you'll get no coincidence because both photons go in a superposition of one way and the other. But as you move the beam splitter, they arrive at slightly different times. That creates distinguishability. And so when the photons are distinguishable, half the instances of two photons getting in will yield a coincidence, half not. And so the rate up here is half the number of times that you send two photons in. And so that's it. And it's a very important technique. Looking at the shape of this is used in standard experiments. One is to show that you have single photons, and the other is to characterize the temporal wave packet or the spectral properties of the photon. So it's, almost every quantum optics lab in the world has this setup built in. And so it's nice. We were able to mimic that effect with microwaves. And then these are the effects. We do our theory and experiment, and so it's not enough just do the theory to say it's classical, but the experiment's done, and we see the effect beautifully. So everything's kind of proven theoretically, proven experimentally, and we were so successful that everybody thinks it was obvious since the 1980s, which it wasn't. Okay. The next work that I did with Urbasi and Simanraj Sadhana was PhD work, was theory. It's published in New Journal of Physics, same year as the other one. And this is double slit interferometry as a lossy beam splitter. So ever since I first met Urbasi, probably 12, 13 years ago or something, when she was in Waterloo, she was doing triple slit. And so I was thinking a lot about slits and how to use them. And so the way I think about it is multiple slit interferometry is interesting to me because it's a way of reaching higher dimensional informational representation. If you do double slit, like a Young experiment, and then if you think about, it could be an electron, it could be a photon, which slit did it go through, then in a quantum information sense, it's like asking 0 or 1, right? And of course, when you demonstrate that the photon or the electron goes through a superposition of two slits, in a quantum information way of thinking, then that's a qubit, a superposition of 0 and 1. So this work I'll show you in a moment. We went to triple slit, but the idea here that I was thinking about multiple slit interferometry as a way of accessing higher dimensional information. So then with Urbasi and with Simanraj, we spent years on this. It took quite a while, but we spent years on it, and essentially we just got right multiple slit interferometry. Send light into beam splitters, they go through. We modeled everything, about the mirrors and beam splitters and phase shifters in the system, and then we developed this post-selected way of showing that this is a lossy form of interferometry. The reason it's lossy is because the way slits work is light diffracts, so the light's spreading everywhere. But if you say, I got a coincidence, you have a detector somewhere, or a coincidence with two detectors, then you kind of just ignore all the light that went in that didn't yield the coincidence. So when we say lossy, in a quantum information sense, this would be called post-selected, means that unless you see something, you just pretend nothing ever happened. So you're really feeding in light into your system, and then you interpret based on post-selecting. So we developed the whole theory for that, and just here's the abstract for that paper. Just to make it clear, I'll grab a few lines out of there. We cast diffraction-based interferometry. Okay, so the slits are about diffracting light in the framework of post-selected unitary description. So this unitary description is what we need to connect it with, say, quantum computing and quantum communication. So the unitary is just the way of mapping quantum states to quantum states. In a lossless way, the post-selected says, if we see something, then we think of something going in. If we don't see something coming out, we pretend nothing went in. So that's the post-selection. And then the idea is to enable a platform for quantum information processing. Various ways to go to higher dimension are things like orbital angular momentum. You can make light into a corkscrew, various other structured light ways. But this, if we get the theory right and we make it rigorous, it gives us a very nice, robust way of doing quantum information processing. And so that was the motivation. And then we go here, the infinite dimensional transformation is just saying there's an infinite number of modes to describe diffraction properly. We truncate it to finite dimension by post-selecting. The finite dimension really refers to the number of detectors. And then we show how to do all this in a classical way. And we claim that it's a robust alternative to multi-beam interferometry. So we claim that this is a path forward to do higher dimensional quantum information processing in a way that works well. And I'm collaborating on some work now that's using some of these concepts, including polarization, not discussed here. So we are managing to push this idea forward in a useful way. Oh, press this. Okay, and this is just a picture of the kind of things that we did. These are two sources. This is a slit. Slit, light goes in the slit. You can imagine Huygens principle, light diffracts through and diffracts through. But if we only care about incidences that lead to detection events, then we imagine our detectors over here, light coming through. And then what happens is we kind of back propagate. If we know light starts at a source and if it ends here, then the number of trajectories that lead to these coincidences is very small. And so that's the trick. We just say, well, out of the infinite number of ways light can diffract through the system, and we say we only care about events that lead to detection, and we know what our source is, we narrow it down to some small number. So this becomes the qubit. Light can come in superposition of here and here. And then we extend, even though we didn't put it in the title, triple slit, and then we start working out all those trajectories that lead to events. Here's 3 slits, sources, diffraction, but we only take the trajectories. These trajectories are like ray diagrams. So you take the rays that matter and post-select. And so we just have this very nice framework for describing this system. And where I find it convenient is then if I write a paper and I talk about multiple slit ways of realizing quantum information, I could just write a sentence and refer to this paper. All the rigor and concepts are built in. And this is a theory paper. Okay, the next one that I'll talk about is, this is the last one that's published by me and Urbasi's group. I'm sure we'll have more coming up. This is the last one in the discussion with Urbasi. And this one, I was kind of set up in Komuti's talk where he kept promising I would speak in detail about this. So I don't want to make him a liar. So I'm going to show the detail, but I won't spend a lot of time on it. So I'm keeping your promise halfway, that the stuff will all flash before your eyes, but I won't go through every step. Okay, so this was published in Physical Review Applied. It's been getting good attention. It's about QKD-SIM, which is a toolkit that we developed here at RRI to simulate quantum key distribution, including imperfections. And where this matters, there's two ways that this tool becomes useful. One way it becomes useful is design, so this toolkit was tested here, doing what's called the B92, the Bennett 92 protocol. It was novel doing this particular protocol, and we used the experiments on B92 to validate the toolkit, the software. And so it's useful in designing the experiment. You just plug into your toolkit what your design is. It'll tell you your bit error rate. It tells you losses, all this kind of stuff, and what key rate you'll get, and so on. And so we developed it and tested it. The other way this is useful, which will be down the road, is when quantum key distribution is being used, and you want to know with your satellite, will I get good key on a rainy day? What's going to happen in sunlight? What if I have 2 submarines underwater and they need to communicate? And you need to know how much secure key you can generate. this tool should evolve into serving that purpose. So it becomes a way of anticipating what the key rates are. And so one of the things with quantum key distribution is you generate secure key, but how many messages you can send or how big a message you can send is a function of how much key you generate. So you want to use that for forward planning. We haven't finished developing the software. It's kind of a slow motion thing at the moment, unfortunately, but I'm sure it'll have value. And so we included the imperfections. And one of the things we did here that makes it nice, distinct from other tools, is the tendency is to say this is all quantum mechanical. Therefore, I will use all the mathematics of quantum mechanics to do the simulation. But it makes everything very unwieldy. So we stripped down the quantum mechanics. Actually, you kind of see a theme here. It was the classical Hongo model, the classical interferometry, and then this is classical. And you're kind of seeing, like, for me, I mean, I believe quantum mechanics, but if I can do things classically, I always try to do everything classically, it's better. It's better conceptually, it's better mathematically, it's better computationally. And so that kind of thing is used here. Okay, so when I keep putting classical in everything, doesn't mean I don't believe quantum mechanics. It just means I find classical mechanics much more convenient. So we developed this technique by making quantum key distribution and what it does as classical as possible. And essentially, instead of dealing with a qubit, we can deal with 2 bits of that. And then we just have these very simple transformations. And then we write all the imperfections in terms of what it would do to the particular states we're creating for generating key. In this case, sorry, my allergies have kicked in, so I'm hay fever around here. Okay, so this just motivates it. Quantum key distribution is important. We need software to model it. And then here, this is about our QKD sim. It says, ultimately aimed at being developed into such a software package. So that's a way of saying it'll happen, but we don't know when, but we're trying. And then we demonstrate the B92 protocol. And then here it just says that we get very good agreement. Experimental, we get 51 kilobits per second, 4.79% quantum bit error rate. The simulation is 52.83 plus or minus 0.36 kilobits a second and 4.79% error. This is really good agreement. This, to a quantum optics person, is good. If you're a 5 sigma type particle physicist, it would look terrible, but we're not particle physicists. This is, for our purposes, that's an excellent agreement. So we get very good agreement between our experiment theory. Uh-oh, why is that vanished? Oh, it's the slides. There must be, okay, I didn't check these this way. Okay, so this is just a background on simulators out there. And so this gives us a context of, that more and more there are toolkits being developed. And so this slide, when it finishes, is just giving you an idea of some recent work. You can see this whole idea of developing these toolkits is becoming increasingly popular. 2 in 2022, quantum parameter estimation, real-time quantum control systems, quantum computing. And this is really a feature of, as we develop quantum technology, it's kind of growing into a strategic area internationally and, certainly here in India. And so, as we move from a pure foundational science perspective into developing technologies, these kinds of toolkits become more and more important. These aren't the only ones, but a lot of groups are developing these toolkits, and some of them actually have commercial value. So, it's possible this would have commercial value. Okay, another blank. Okay, so let's go through it step by step. So this is another QKD simulator for context, etc. So it just gives you an idea that there are other people out there doing these kinds of simulators, but not what we do. So usually when they're doing all these kinds of things, they're doing simulators how they would work in a perfect world. Our goal is to simulate in the real world so we can make these predictions. How many are there? Okay, I think that must be it. Nope. Okay, and then what's missing in all these kinds of things is quick and precise simulation of physical processes. So as I said, our work is tested against experiment, and the quickness comes out of making it as classical as possible, but not too classical. and consideration of non-ideal effects in experiment. So that's the advertisement. This is how it works. So we have a flow. We use a waterfall agile method. So there's techniques for software development. So we use those to make sure that we develop the software according to software engineering best practice. All the kinds of things we care about, the optical and electrical components, random number generator, time tagging, all these kinds of things are built in. So we're really simulating how it works, the noise that goes on in the system, and so on. So these are just showing you the kinds of realistic effects and where they fit into the architectural design. So we're using proper software engineering practice to design this. Okay, and then it was tested on B92, and then this, I just said it from the abstract, but this is just showing you again the key rates, the quantum bit error rate is a percentage key symmetry, and for our purposes, we think this is excellent agreement. It's good enough to plan the use, to plan things and anticipate how much key would be generated. Okay, that's it. User interface, patenting in progress. That's actually, so there's a patent, an Indian patent filed for, so it's been filed, and then we'll wait for approval, I hope. And then this is the interface to be able to use it. Okay, so that ends the summary of the stuff I've been doing with Urbasi, and now I'll talk about the stuff that I've done with Andal. So Andal and I met probably around 2009. She did a sabbatical at the University of Calgary, group of Alex Lebowski, who used to be in Calgary. He's now at the University of Oxford. And so Andal came and visited for a year, and she got into all these electromagnetically induced transparency experiments, and this has been a long interest of mine. So while she was in Calgary, we started talking, and then she was doing experiments on 3-level atoms. So you have some sort of 2 ground states, hyperfine splitting, I'll show it in a moment, then there's a higher level, and then we want to be able to drive processes, kind of Raman-like, but not for Raman type transitions, but more drive a transition. And then what you want to do is to switch an absorption to non-absorption. So by driving one transition, you can do a split of a level, often called AC Stark shift. Technically, it's an Altler-Towns effect, and then make it transparent. So it was this kind of idea. And then over the years, I started thinking a lot about, so you have this 3-level system and you drive and drive. And I was thinking a lot about what if we add another driving term, which is microwave, between the 2 hyperfine levels. So this 2 ground and 1 excited, this is called a lambda electronic structure because it looks like the capital letter lambda in the Greek alphabet. And then if you drive the lower transition, it looks a little bit like a delta. So years ago, I named this a delta atom. So here, the idea of the delta is it's 2 lower levels, hyperfine splitting, and 1 excited level. And then turning a lambda to a delta is just adding a microwave term to drive that. And there's a lot of richness to it. And certainly when I was thinking about this years ago, there was like maybe 1 experiment out before that had looked at it. Just people weren't thinking about all the effects. And then with Andal, and we talked about it, she started building that. She got her microwave cavity in the lab. And so she developed a system here at RRI to be able to drive optically and the microwave transition really well. So it took a while, but every experiment I'm going to tell you done in her group is related to this driving, turning a lambda to a delta is how I think about it. And so here's the group and Andal, and it's the experiment. I don't know why she usually last author is an honorable position, and I don't deserve to be last author here. The 99% of the work was done here, but somehow I wound up last author. Okay, and then there's a whole list of addresses, most of them mine at the time. Okay, and that was published in PhysRev A. And so here, the idea is phase-sensitive amplification of electromagnetically induced transparency. So by driving 1 transition, we turn absorption into transparency. That's what this is about. And then by making a microwave field, we decided to investigate if we could use the phase of the microwave field to control the electromagnetically induced transparency. And as a bonus, we also get amplification. And so, ground state coherence decay, because we're driving with a microwave field. we found it was robust, so there was losses and all that. We found that the kinds of effects we were looking for really stood up well against experimental imperfections, noise, and so on and so forth. And so we realized, and this is actually something that I proposed in superconducting systems. So I was before this, I was thinking about ways that we could incorporate memory into superconducting circuits. So the original delta idea was a way of trying to build quantum memory into superconducting quantum computing, but this was the first experimental demonstration of the idea. And what happens is the microwave field through that driving doesn't just switch between absorption and transmission, but it can go from absorption to amplification. So we can use that microwave drive to add energy to the system, which is kind of nice, because if you think of, even when you make the medium transparent, there'll always be a little bit of loss. And by tuning the phase, we're able to compensate loss and get amplification. Of course, noise has to creep in, but it's still a potentially useful effect. And then here, this is the 3-level system. Think of hyperfine splitting. Excited, we have a detuning that we allow. We can tune the detuning. These gammas represent decay processes. So, if you know your Einstein A and B coefficients, these are related to the Einstein A coefficients. And so this is the lambda structure that's very well studied for decades. This is the addition that Andal and her group put in, which is the microwave drive. And this is a theoretical picture. This is the angular frequency. So h bar times that would be the energy separation from here to here. And the capital omega is the Rabi frequency. The Rabi frequency is the electric dipole moment dot product with the local electric field divided by h bar, or h cross. And so that's the Rabi frequency. And so these are electric dipole transitions, and this is a magnetic dipole transition. It's going on through the microwave field. And then we set it up to have a sum frequency process, and we discover enhancement, gain, and absorption of the probe field. All kinds of nice effects that came out of this that hadn't been seen before. And down here, this is just capturing the temperature of the system, and the decay rate, gamma C, was here, gamma C. And down here, anything below that 0 line turns out to be amplification. So we were able to observe in the experiment that amplification. Then we went on from there 3 years later. This is 2017. We started to make it into a switch. So, we're in that first experiment, we're seeing the microwave-controlled electromagnetically induced transparency with a bit of amplification. And then in this experiment, and then you can see I won the argument. I got demoted here to second last author, and Andal appropriately is last author. And then this one, we pushed further where we wanted to be able to control the switching. So we turned the microwave field phase. By controlling the phase of the microwave field, we can jump back and forth, so we can make an optical switch. So that was kind of fun. Here you can see a delta system at room temperature. We used rubidium-85, the D2 manifold, so it's a particular common line in alkali atoms. And then, Rabi frequency, remember, so that's essentially the dipole dot electric field of a microwave drive field, exceeds that of the optical probe field. So we push the Rabi frequency up, so it tells us the flopping rate between 2 levels. We can get three-wave mixing nonlinear interactions. So we have basically it's just saying, here, this is the Rabi frequency. So if we make that strong, the Rabi frequency tells you how fast the electron goes back and forth between 2 levels, how fast it goes. So we can get a nice transition when this is going faster than that. That's what this is saying. And so when that happens, we get this nonlinear behavior, and then we're able to make a switch. And then here, these are the experiments showing how we switch between an absorption line and then electromagnetically induced transparency. Cuts, basically, this is Lorentzian. And if you get real electromagnetically induced transparency, you get a negative Lorentzian cutting through this. The negative Lorentzian is really a Fano interference effect. So it's Fano, I think, got a Nobel Prize for that. And basically, it just comes because 2 levels share the same reservoir. And then our switching was very sharp. So you can see we switch our microwave field between two levels, and we're able to go between absorption and transmission. And then then there was this one where we did phase-sensitive amplification of an optical field using microwaves. Here I got demoted to third last author, so one day I'll be first author. I'm going to work my way down. So we did this, and this was phase-sensitive amplification of near-infrared electromagnetic field. We all work everything at room temperature, rubidium-85, and so there was a first demonstration over here. This is CBC is coherent beam combination, some frequency generation, and we're just seeing amplification effects. This is a gain, and it's really just showing you we have excellent control over gain in the system. And then the final work with Andal, this is out last year, microwave-driven generation and group delay control of optical pulses. So in this work, and I should mention, Fabian Brettnacher has been out a few times, so he's another, I don't know if he's still coming back, but he's another regular visitor to RRI. So this makes use of the cyclic atomic level scheme, that's still the delta, with optical and microwave field controlled. And basically we want to be able to slow down a pulse. So electromagnetically induced transparency has the property that you can slow light down. And in fact, back in the 90s, Lida Howe, she's at Harvard University now, her student postdoc work was stopping light. So we've been able to stop light, make the group velocity 0 since the 90s. And so this is a descendant of that concept, to just slow light down. And so at the few-photon optical level, we make use of this, not just to switch between absorption and transparency, but to slow light down. And then this shows the results. Hybrid second-order nonlinearity to generate optical pulses. So we make pulses that have fewer than one photon on average through a thin sample, and then group delay that we're able to get. And there's the delay that shows that light slowed down. So that was my last slide. And I'll just summarize. And I'm on time, so it's good. And no questions, that's amazing. Oh no, just hang on, no questions. No, I almost finished. Just let me finish and then take the questions. So this is known as delayed gratification. So I just want to summarize by saying, so it's been excellent here. Actually, there's a lot of other groups here that I talk to that I'm really amazed by quality, just a finite amount of time to do everything. But over the years, between Andal, who I've known for many years since she spent time in Calgary, and working through, we did a lot of the nice work on this delta system. Andal's fairly conservative. So I feel like some of the work is I like it a lot. And then we debate journals and all that kind of stuff. So she's very happy with sending to really solid places. I think some of the work we did, represents a good advance in coherent population trapping and all that. And then with Urbasi, it's been an amazing journey because we've pushed forward really on a lot of fundamental techniques that will be useful for quantum information processing for the quantum cryptography. And everywhere from this software toolkit to robust platforms for things like new robust techniques for quantum cryptography, which is part of the time spent here. And so working with both of them has been a really good journey. And I'm hoping somehow I can keep coming back and continue these collaborations and maybe even be able to, get my hands into some of the other beautiful experiments going on. Okay, gratification delay over. Thanks. So there's this one and this one. So.
Thank you, nice talk. And I was wondering, this classical simulation of a quantum, do we have any other way to do it now? We always have to do it that way, I think, right? And so, also, what is the big challenge there, I think?
So you're asking about the classical simulation of the Hongo mantle dip, right?
Yeah.
Is that correct?
Yeah, correct. Quantum system, we don't have any other way to put it in the present computers to simulate them, right?
I'm not sure I understand the question. So the idea of the Hongo mantle dip here is that we think of it as quantum, photon goes in, but with Urbasi's experiment, she controls the relative phase. So essentially we can treat it classically by saying that we can set up if the phase shifts by pi, we can get destructive interference. If they're on phase, we get constructive interference. And this way we're able to mimic the no coincidence. So that's the classical here is not about simulation. In this case, the classical is saying the standard belief up until recently that two photon coincidence perfect is zero coincidence is a signature of quantum is not correct. So the purpose there was to say what you think and what's true are different. So that was it. But then you might be asking about the this QKD sim. And then in that case, in that case, you say, I'm going to simulate optical generation, single photons that are polarization encoded or something like that. And then you think, everything about quantum key distribution is quantum. So I got to use Hilbert space, vectors in Hilbert space, and unitary operators. And then in that case, it will work, but it will be computationally bigger overhead. So in that case, we're looking for ways, we just want to get the software to work as simply as possible. Easier to understand, easier to correct. So when you asked about the classical, those are the two sides. So one side is classical because we're trying to remove misconceptions about quantum. And the other side about classical is we're saying, if you have a task like quantum key distribution, don't waste your time developing, something that will solve everything. Focus on solving that.
Connected question is, I think that topic, that what you mentioned, removing the misconception about the quantum, that itself is worth a topic of a paper, right? Like it's because people.
Sorry, what?
That itself, how do you simulate? How will one simulate? This tool as such is a useful thing, but what is the methodology that one has used? That concept itself is a very useful information.
For which one? For that Hongo mantle dip classically? Or for the...
This one, yeah.
Oh, okay. What's the method that's used? I didn't put up a block sphere, but let me try to... But it's there. That's a good paper. Is that what you want? Yeah, I mean, yeah, so if you're just saying it's topic for a good paper, I think that's a good paper. If that's the point. That's the... You need a mic, otherwise nobody hears you. Your mic is right behind you.
No, I'm fine.
No, it's right there. He's trying to hand it to you.
Thanks, Barry. So I think this is a 48-page paper. So part of it is the methodology and part of it is actually the algorithm. So we combine everything. And of course, there is the whole experiment, right? So he thinks that we should have split it up, but...
Is that right?
Split it up into...
Yeah. No, I write...
No, it's fine this way.
You should see my quantum algorithms papers. They're 80 or 90 pages. So this is short to me. Yeah.
If we use two sources, double slit setup and two detectors, will we still get a Hongo mantle dip?
You're saying if we use two sources and
a
two detectors.
Double slit setup and two detectors.
But that's what that is, right?
In the
two sources, two detectors.
Yeah, but not a beam splitter, a double slit setup.
Oh, now I get it. Okay, yeah, you're saying, okay, so in this case, we show with microwaves that, we can mimic no coincidence by making these phased or anti-phased. And then you're saying, can we do it in the context of this experiment?
Yes.
Yeah. And so in that case, absolutely. Yeah, if we think of a classical light pulsed and we phase or anti-phase and detect, we should get the same thing.
So we would still get a Hongo mantle dip. Even if we use a quantum source or simulate classically, you're saying
that's the point. So the reason that the misconception that the Hongo mantle dip is limited to 50% is because in the optical domain, we don't have the phase control, right? So if you think of a pulse of light like this, it's got a carrier wave inside. Now, in the optical domain, we don't have a way of controlling the phase of the carrier. So the reason that people think that they'll get a maximum 50% dip is to believe that control isn't there. When Urbasi's group moved that to the microwave domain and made pulses, you can control the phase. And that's something I mentioned with Andal too, with controlling the phase in the microwave allows us to get a lot of effects in the delta atom. So it's very beautiful combining microwave and optical. So that's what you control. So the Hongo mantle dip should work that way. The only reason the 50% dip comes is if you believe you can't control that relative phase, then you can't beat the 50%. But that's a limitation on control. That's not quantum.
So I have a question related to the delta system, the experiment and the theory,
So later.
where there is the data presented with the.
Oh yeah, this time.
Later.
Tell me when to stop.
Yeah, on
But
next.
one?
No. After this. Yes, this one. See, for example, the phase is varied, and then you look at the gain. Means this is very nice that there is a gain of the order of 5 with the phase.
Yeah.
But so what might be the difference between the experiment? There is a slight discrepancy with the, because these experiments usually are very precise. So
Yeah, it's a good question. I wish Andal were here because I did the theory. Okay, so the theory is perfect. So we need the experimental. There's nothing wrong with the theory, and she's not here. So it's a good question, and maybe we wrote it in the paper. I was trying to catch up on everything, and I think we wrote it, but I don't have it handy at the moment.
Mhm.
But I think we did discuss it, and I'm sorry for my forgetfulness.
With a population inversion or without population inversion?
So we don't do population. You're thinking more like lasing, right? Population inversion. No, we just drive. So in the typical system with EIT, you have the probe and the control, and then what happens is we'll drive strongly one. So the way to think about it is the way the system works is if you drive strongly with one field, you split a level. That's the Adler-Towns effect, often mistakenly called AC Stark. And then when you split the line, if the two lines, it's called Drest field, but if the two lines effectively under that driving, both decay in the same reservoir, you get your electromagnetically induced transparency. So this is not population inversion. It's called coherent population trapping. If you switch to a different basis, you find that that a superposition of these two levels is what's called dark. So you find, well, too much to explain, but there's no population inversion, but there's a whole area, quantum optics, known as coherent population trapping. And that's what goes on. It kind of drives the coherence and prevents some transition from taking place. And then what we did is, that's in the textbooks. It's with no coupling in the hyperfine levels. And then adding that, actually it's really interesting. I mean, I've had debates over the years. So there's a whole textbook approach to electromagnetically induced transparency. And if you read and believe what they write in textbooks, you would never think about these things. And so there's this whole literature on coherent population trapping and blah, blah, blah. This is just what it is. Like the way I think about it is we just create the system, there's interesting effects, and the way that the textbooks say it, I never really liked and I ignore. I don't know if it answers your question, but that's my thought on it.
Amplification in the probe transmission also.
Yeah, we amplify the transmission. So what happens is we drive one. I keep thinking this probe and control are swapped, so I'm a little bit confused at the moment. But yeah, we drive one to split the level, and then that switches between resonance and off resonance. So the way that you slow light, or you trap light, or switch between absorption and transmission is by splitting and unsplitting a line and having the split line decay in the same reservoir. And then what we have here by driving this coherence is it turns out that some of the energy here can get built up in another transition. So instead of going between absorption and transmission, we can include absorption and amplification and be able to control those. And then the whole way of thinking with population inversion, coherent population trapping, that kind of thing, it's not the way I think about it. I just write down mathematically the system, and I have my own way of thinking.
Can you clarify the connection between the lossy beam splitter and post-selection? Because by lossy beam splitter, generally we would understand something which would introduce a systematic error in the experiment, and post-selection is something which the experimentalists do after the data is recorded.
Yeah, okay, I know what you're saying. Okay, first of all, there's kind of you can always introduce a bias by post-selecting. So if I go to Las Vegas and I bet on the roulette wheel, red or black, and then I only post-select on the times I win, so I always bet red and I ignore every time black, I will get rich. It's obviously a bias, right? If you go to gamble on something like that and there's no house advantage, you'll break even. But if you post-select only on the things you want, then you can bias it to look like you're getting rich. So it's kind of an example of what you're saying. So if we aren't careful about it, then, like if we're saying we're post-selecting and we game the rules, then it doesn't represent properly what's going on. In the way we set it up, we're not gaming anything. We're just saying we set it up so that we have our detectors. There's the symmetries in the system, the two slits. And so the way it works is that it's post-selecting based on the source light getting to the detector. As you know, it diffracts, so some of the light misses. And then this is where we don't want to game the system. We don't want to say that we're somehow post-selecting only in certain instances. We're just saying in these cases where the diffraction trajectory goes that way to that detector, then it counts. And so everything is designed here not to bias it, not to do anything. Everything is set up so that it completely replicates a beam splitter it replicates the beam splitter behavior, and everything we ignore is not biasing at all. It's not making anything weird. You know the Huygens wave, right? So it's just saying, if you take a Huygens principle in optics and you get your spherical wave coming out, and then you just make your rays as perpendicular, and then we're just saying we only ever see light traveling on those rays.
So this is related to the slow light work. So you are reducing the group velocity. So can you say like how are you controlling the group velocity, and can it make faster?
Oh, you mean can you speed up the speed of light? That's an interesting point. Okay, so can I say it again? I'm not an experimentalist, and you're testing my weaknesses. But I mean, whatever this says, like these are the, I don't remember how much slower it is. I can't remember the number, but we get slowing, and I just didn't, I wonder if it's in the abstract actually. No, we don't say it. Okay, no, I don't have the number, sorry about that. Can we speed up light? So there's some interesting physics here. So first of all, like what does it mean to talk about group delay? What is the speed of light? So if you just have monochromatic light, the speed of light is c. And then if you have a refractive index, you can modify accordingly. But when we start slowing light down, we're not talking about c over n, where n is the refractive index. We're dealing with the group velocity. And the group, so if you have little omega over k is how I think about the phase delay. And then d omega by dk is the inverse of group velocity, something like that. And that's part of a power series expansion. So even talking about how fast light's moving only makes sense if you can truncate that expansion of higher order derivatives. Can we speed it up? There's literature that says yes. I don't know, you know this, right? That's why you asked. Ephraim Steinberg at Toronto, he did his PhD in Raymond Chow's group at Berkeley, and his whole PhD is about speeding up light. So they do this experiment where they get a classical music piece, and then at the other end there's like a speaker or something, and so they're able to send the light faster than the speed of light, so you're playing this musical piece faster than c. So obviously it's acausal. And why does that work? And the answer is because it's so birefringent. It's, basically they make a stack of plates, and then a pulse starts to be like this. It's got wobbles at the front, and then they make the detectors so they have assumptions that based on the front end of a messy looking pulse, they extrapolate what note should be played. So if you ignore the requirements of a convergent series of higher order derivatives. And if you make assumptions about some sort of analytic continuation of the leading edge of a pulse, then you can have results that manifest as faster as speeding up light. But we don't do that. So here everything is really well defined in terms of group velocity when it makes sense to do it. And then all we can do is slow things down. I mean, there's also what's the effect in Cherenkov radiation? That's another example of speeding up. So no, we don't do anything like that. Maybe these things are possible, but I'm much more of a boring person. Like, you know, it's like really well defined here, not that kind of stuff. I like that stuff, but it's not my style.
There are no other questions. Then let's thank Professor Barry Sanders. So I have a few announcements to do before we formally close the session. First of all, it was wonderful to have this Showcasing RRI event over the past 1 week, where we heard talks from practically every group of RRI, starting with early universe and then giant atoms, hybrid ion atom systems, spins at ultra low temperatures, quantum communication, very exciting stuff, and then going to ultra fast phenomena. From the soft condensed matter, there were active matter, and then there was liquid crystal display. Then there was very exciting biophysics and non-Newtonian fluid related talks. I enjoyed every moment of it. From the astro, there were binary systems, X-rays, and then high magnetic field, very exciting observations, what was happening, and also from technological side as well. From the theory physics, there was a lot of interesting discussions in non-equilibrium statistical mechanics, then topological insulators, and then of course on the quantum gravity aspects as well. So did I forget anything? No, I think I was attending most of these talks. These were really enriching, and this also is an event which tells us that we should do this kind of event more regularly. Maybe we'll take this up. This also formally the beginning of the 75th year celebration of RRI. So we started with the Platinum Jubilee launch event. So I thank our director, Professor Tarun Shorodip, for initiating this event. This started with a lot of enthusiasm, and there was a fantastic event in the lawn. And this is one of the first, if I remember. My stay in RRI is so far short, but still this is of a new era. And I thank my colleagues in the Platinum Jubilee Committee, Professor Nayantara Gupta, who is the chair of this Platinum Jubilee Committee, and then Sumati Surya, Sanjeev Shabapandit, Professor Sadiq Rangwala, Pramod, Shantan Majumdar, Saurabh Singh, and then all these events would not have been possible without Subramanian. This is a big thank to Subramaniam and Bani, who is not here. So these are the people who had made this event possible. And then I must thank the local organizing committee with our administrative officer, Mr. Naresh, and then Mr. Sachin Belwadhi, who had done wonderful work to get this going, and Manjunath, Gayatri, and then security officer Manjunath and his team, Savita, Chaitanya, Mahima, Ritik, Anish, and Sundareshan, Suma, and other administrative staff. They have put in a wonderful effort. I know that the last Sunday they had worked till midnight to get the event started. So this is something which tells that next day morning we came and we saw that it's a different view. And of course the IT team and estate and building team, Chetan, Munisharan, Mahalinga, and other staff members. So this is really a big thanks to everyone. I wish everyone was there. And then the chairs of the different sessions, they have done a fantastic job. Rahul, Aditi, Sonali, Suraka Bhattacharya, Vishnu, Rahul Sharma, they had all chaired the different sessions over the past few days. Okay, so IT team, I just mentioned, okay, the names are Jacob, you all know Jacob Rajan, Sridhar, Ranjit, and Faninder. Then Ganesh, Narendra, Naveen in the auditorium, they have really maintained everything properly. Canteen staff, they have put in a lot of effort, Velu and his team. So all these people were behind this seamless show of event, which was, at least I think this was a grand success and starting of new era. Now some upcoming Platinum Jubilee event, I would like all of you to mark your calendar. The next event will be December 6 to 7, which will be organized by Professor Urbasi Sinha. This is a very interesting Women in Optics and Photonics in India 2022. This event will take place in RRI, and then I would actually encourage if you have not registered for the event, especially the women members of RRI to register. And then the first of the international conferences which will take place, this is named Frontiers in Cosmology. This will be 27th February to 3rd March. I would like to mention that, though this is Frontiers in Cosmology, but I think all group members should try to attend because that will make the event a lot of success. 27th Feb to 3rd March is? Oh, I'm sorry. 20 to 24th Feb. Sorry for this, this printout. Okay. Okay. So, but anyway, all this information is there in the RRI website. So then there is a major outreach program on National Science Day that will be on 28th February 2023. Then there will be Raman conference on light and matter physics, very much in the theme of Professor Varichandra's talk. That will be 14th to 18th August 2023, tentatively. We are trying to fix the date around that time. Then there will be a quantum gravity conference at RRI from 4th to 8th September 2023. Then Frontiers in Physics of Soft and Biological Matter, that will take place between 25th to 30th September 2023. And then on November 7th, exactly 1 year down the line, we'll have the main Platinum Jubilee anniversary event. And I hope that there is a lot more enthusiasm than this time, which is difficult to beat actually, what happened this time. And then there is one more event, Frontiers of Statistical Physics, that will be on 4th to 8th December 2023. So these are the events lined up. There is a lot of exciting time ahead. Wish to see everyone to attend all these events. So with this, I would like to say that this event comes to a formal end, showcasing of RRI and launch of the Platinum Jubilee or 75 years of RRI. So again, thanks all of you, and I thank all the speakers and also the audience for this enthusiastic showing off. Thank you.